How do things get heated up to the point where they catch fire? Like an Apollo spacecraft re-entering the Earth's atmosphere. Right. Here, it's friction. The work of air particles pressing and rubbing against surfaces that are moving at tremendous speed. And it's friction that produces the heat that lights matches. You can use metallic sparks for ignition. Electric sparks will ignite flammable gases, too. There's at least one more method of ignition. If you've ever pumped up a bike tire with a hand pump, you've probably noticed the heat the pump generates. If you could put hundreds of pounds of pressure on it, the metal would get hot enough to burn you. What happens is that the increased pressure crowds the molecules together so that they collide more often. It's a form of friction, again, producing heat energy, actually enough to ignite fuel. It's called compression ignition, and is the principle used by the diesel engine, invented by a German engineer, Rudolf Diesel, over 80 years ago. Today, you find diesel engines everywhere, wherever there are big, tough jobs to be done. The huge highway haulers and buses, cross-country locomotives and little switchers, too. Boats, ships, and harbor dredges. Earth movers, agricultural and mining machinery. Construction jobs, driving air compressors and operating cranes. And for driving electric power generators for both regular and emergency service for hospitals, broadcast stations, and telephone systems. Because a diesel engine is an internal combustion engine, it looks rather like a gasoline engine. It has pistons, valves, connecting rods, a crankshaft. The pistons go up and down, and the crankshaft goes round and round. In a 4-stroke cycle or a 2-stroke cycle diesel engine, there are the repeating stages of intake, compression, power, and exhaust. But that's about where the similarity ends. The diesel is a simpler engine with fewer parts. It does not have, nor does it need, many of the familiar parts of the gasoline engine. First of all, the fuel is different. It's not gasoline, but fuel oil, or diesel fuel as it is sometimes called, a refined distillate of crude oil. It costs less than gasoline. There are no spark plugs in a diesel engine because ignition is by the heat of compression. Without plugs, there's no need for electrical parts such as a spark coil, wires, distributor, or electronic ignition components. You won't find a carburetor on a diesel either. Instead, each cylinder has a fuel injector. It sprays the fuel into the cylinder. A 4-stroke diesel engine operates with the same cycle as that of a 4-stroke cycle gasoline engine. Intake draws in a mixture of fuel, gasoline vapor and air in the gasoline engine. It's air only in the diesel. Compression comes next, much higher in the diesel than in the gasoline engine. Ignition occurs near the top of the piston travel when fuel is injected from the injector, producing the power stroke. The exhaust stroke drives the burned gases out of the cylinder, and the cycle repeats. Many diesel engines are designed to operate on a 2-stroke cycle, which has several advantages over the 4-stroke type. The 2-stroke diesel works without intake valves, but does use regular Papa-type exhaust valves in pairs. Ports are used for admitting air into the cylinder, air that is supplied by a blower. And that's it, the basic parts of a 2-stroke diesel. Let's see how they work together. At the bottom of the stroke, the exhaust valves are open, the ports are uncovered, and air is pouring in, driving out the burned gases from the previous stroke. As the piston rises and closes off the intake ports, the exhaust valves close. Compression now takes place, high compression. The amount the air is squeezed ranges from 1/12 to about 1/20th of the volume it had when the piston was fully down, depending on the size of the engine. The compression ratio can thus be from 12:1 to 20:1 in different diesels. As the air is squeezed, its pressure rises to between 400 and 600 pounds per square inch. The fuel in the injector must therefore be at even higher pressure in order to enter the cylinder. At the top of the stroke, maximum compression, the air's temperature shoots up to about 1,000 degrees Fahrenheit, well above the fuel oil's ignition temperature. Consequently, when the injector shoots its spray of fuel oil into the cylinder, it ignites immediately, spontaneously. The heat energy thus released provides the power that drives the piston, connecting rod, and crankshaft. As the piston nears the bottom of the stroke, the cycle starts all over again. You can say that the two strokes are compression, power, compression, power. The two-stroke cycle is well suited to the diesel-type engine. One benefit is high torque, the crankshaft's twisting power. With it, the engine takes on additional loads with little or no loss of speed. Also, with power being delivered on every other stroke, there is smoother performance than in a four-stroke system. In addition, there is rapid acceleration because of the frequency of the power strokes. Each cylinder has a fuel injector and usually 4 valves, operated by a camshaft that is driven by the crankshaft. A 2-gear drive would call for very large timing gears, as they are called, because of the distance between the shafts. An intermediate or idler gear solves the problem. Some engines use a chain drive for the same reason. The gear ratio is 1:1 in a 2-stroke engine because the valves and the injector must be operated once for each revolution of the crankshaft. This gear system is also used to drive the blower, which is a positive displacement air pump. It provides an even flow of air to all intake ports. The exhaust valve train is similar to that in a gasoline engine. Cam, cam follower, push rod, rocker arm, and valve. As in some gasoline engines, some diesels have an overhead camshaft, which eliminates the need for the push rod and its cam follower. Whichever type is used, the system operates in the same way as in a gasoline engine, with the springs serving to return the valves to their closed positions when the cam action is completed. The heart of every diesel is the fuel injection system. Some engines have a central high-pressure pump and high-pressure supply lines to the injectors, which are operated mechanically by a cam system. Return lines carry the unused fuel back to the supply tank. In another system, the fuel is pumped under low pressure to a common fuel supply pipe that feeds individual high-pressure pumps, each pumping a metered amount of fuel to one injector. A third type uses unit injectors. Each injector is also a high-pressure pump. A low-pressure pump supplies all the injectors with fuel oil from the supply tank. A return manifold carries the unused fuel back to the supply tank. Each unit injector is a highly precise mechanism that delivers a small but highly exact quantity of fuel to the cylinder at the right moment in the cycle. The injector is operated by a cam, push rod, and rocker arm mechanism similar to that in the valve train. The principal parts of the injector are the plunger, which does the high-pressure pumping, the follower and return spring, a rack and gear for rotating the plunger, the injection valve, and the spray tip with holes nearly as small as the diameter of a human hair. The control rack is positioned by the throttle. Turning the plunger regulates the amount of fuel that is injected on each stroke. A governor controls the idling speed and the maximum speed of the engine. When the cam raises the pushrod, the rocker arm presses the plunger down, first admitting fuel to the chamber, then cutting it off, thereby exactly measuring or metering the flow to the exact quantity required. The fuel oil is pressurized, up to as much as 20,000 pounds per square inch, so that it opens the injection valve, allowing the fuel to flow out of the spray holes. To prevent leakage under the high pressures, the clearances are extremely small, down to only 50 millionths of an inch, making the unit injector one of today's most precise mechanical devices. Like gasoline engines, diesels must be kept cool and lubricated to prevent damage from friction and heat. The cooling system is a kind of jacket of water or antifreeze coolant surrounding the cylinders and piped to a radiator. A pump circulates the coolant through the system so that the radiator can remove excess heat from it. A fan assures the proper flow of cooling air through the radiator, just as in a gasoline engine. Engine lubrication is provided by oil. It is pumped from the engine's oil pan up through the bearings, the crankshaft, connecting rods, and piston pins, from which it flows onto the cylinder walls and drops back into the oil pan. The system also lubricates all parts of the camshaft system and the blower drive mechanism. A cooler keeps the oil from being overheated by the hot parts of the engine. An electric starter motor is usually used to crank the engine, using power from a heavy-duty battery. A generator or alternator keeps the battery charged. Today, diesels are available in sizes suited to any job, large or small. They may have from 1 or 2 cylinders to 6 or 8, or even 16 cylinders in the same unit. Rotating speeds, RPMs, may be low, medium, or high. There may be 1 piston in a cylinder, or 2, with a common combustion chamber. Cycles, 2-stroke or 4-stroke. The cylinders may be inline, V, or radial. Diesels are larger and heavier than equivalent-powered gasoline engines. The stronger construction is needed mainly because of higher internal pressures resulting from high compression and compression ignition. Because of its size and weight, the diesel engine is more costly. It does not provide the flexibility, quiet operation, and performance preferred by most passenger car buyers. Diesels have definite advantages when used in heavy-duty applications. First is greater efficiency, much greater than can be gotten from any other type of heat engine. Next is fuel economy. Less fuel is required to produce the same amount of power at the shaft. Also, a wide range of fuels can be used, depending on engine size and design. Diesels also have another advantage. They are low emitters of air pollutants. If you see some that produce objectionable smoke, it means that the engines are old and badly worn, or that they need good maintenance or overhaul. Diesels are the strong guys in the engine field, working hard for long hours on end and doing it most efficiently and economically.
country today glide diesel-powered trains. Travel triumphs of comfort, convenience, and beauty. Effortless speed, born of vision and faith. Gleaming streaks of power have caught the imagination of Americans everywhere. Electricity and gasoline have brought the 20th century far. Diesel power will carry it forward. The romantic way for Americans to travel is by rail, and diesel-powered trains make people want to ride on trains. Diesel-powered trains get passengers from one place to another in a hurry, in calm, quiet comfort. Diesel-powered trains are giving modern America modern transportation. They have proved their worth in regular service, trip after trip.
Diesel-powered trains are leading America into a new era of rail transportation. But the idea of an internal combustion engine for railway locomotion is not new. Interest in the internal combustion engine produced the engine in the early automobile and looked to its application as rail motive power. This mutual interest produced in 1905 the McKean car, manufactured by the Union Pacific. Powered with a 150 horsepower gasoline engine, it carried baggage and passengers. In designing the McKean car, the Union Pacific staff took some ideas for reducing wind resistance from the Baltimore and Ohio Adams wind splitter of 1900. Another important contribution to car design made by the McKean effort was that the structure was very strong in proportion to its weight. About 1909 came a gas-electric rail motor car. This car differed from the McKean car in that it reflected the progress that had been made since 1905 by the automobile manufacturers. The rail motor car of 1909 proved that electric transmission was a most important element in this form of transportation. The gas-electric rail motor car grew steadily in horsepower, utility, and dependability, paralleling the development of the internal combustion engine in the automobile. Until by the end of 1915, between 90 and 100 of these rail motor cars were in operation in the United States. During the war, very little was done with the problem of fitting the internal combustion engine to railroad service. But sufficient interest had been created by the electric transmission rail motor car of 1909, so that in 1924, the Electromotive Corporation found the railroad industry waiting for its first internal combustion rail motor car. Electromotive Corporation showed conclusively that a rail motor unit of sufficient size and horsepower could be built, and that it would mingle successfully with conventional railroad locomotives and cars. Horsepower stepped up from 175 to 900. Rail motor cars hauled combination passenger and freight trains on branch lines. Railroads paid $40 million for over 700 of these locomotives, 500 of them supplied by Electromotive Corporation, all powered with engines built by Winton. In 1929, Chicago Great Western Railroad brought out the Bluebird, its power plant manufactured by the Electromotive Corporation. Smokeless, sootless, cinderless, luxurious rail transportation. In 1933, after constant improvement, the internal combustion engine had approached even closer to its ultimate perfection in the automobile. Likewise, the internal combustion engine was meeting with favor for railroad service. In February of 1934, the Union Pacific City of Salina, the first streamlined train in America, powered with a Winton distillate engine, sped on its maiden run. The three-car articulated train gathered headway with the smoothness of an ocean liner and the speed of an automobile. The city of Salina was the railroad's challenge to all other kinds of transportation, a challenge powered by an internal combustion engine. Railroads recognized the importance of the internal combustion engine as motive power. By early 1933, General Motors engineers had produced a two-cycle diesel engine with unit fuel injectors suitable for mainline locomotive service. This engine was light enough and small enough to permit placing sufficient power to handle a full-size train within dimensions that can go anywhere on a railroad, such as through existing tunnels. The first train powered with this two-cycle diesel engine was the original Zephyr of the Burlington route. In April 1934, the Zephyr made its first trip. This train and the Union Pacific city of Salina everywhere were pointed out as hailing the dawn of a new age in rail transportation. The railroads had the very real problem of winning passengers. The solution was to offer speed, low fares, comfort, and attractiveness. And that solution was streamlined trains powered by diesels. Those who are fortunate enough to get reservations every day over many lines ride 19,420 miles, swelling the 7,115,683 miles. Miles that the railroads equipped with diesel-powered trains have piled up since 1933. The public cannot resist the attractiveness of these colorful arrows. Smoothly, certainly, diesel-powered trains accelerate. In a flash, they are underway. Easy starting and rapid acceleration are important factors in economy of operation. The interiors of these diesel-powered trains link swiftness of travel with truly fine living. Smoothness of operation and the absence of noise relieve the passenger of any sensation of excessive speed. Sleeping accommodations on these diesel-powered trains are distinctive, complete, and luxurious. The traveler sleeps to awake rested. New standards of beauty and comfort are set in the rich appointments of the dining cars of these modern diesel-powered trains. Passengers in the chair cars ride in the luxury of deep cushioned reclining seats, smoothly at 10 miles an hour or at 90 miles an hour. The cocktail lounges of these finest of trains are smart, sparkling, gay with ease and color, informal. All this luxury of travel, this beauty and comfort that has boomed railroad travel, speeds over the rails behind these powerful and economical and dependable locomotives of from 600 to 5,400 horsepower, propelled by General Motors diesel engines, connected directly to electric generators which supply power hour after hour at low cost, without soot, without cinders, without waste. Today, diesel-powered trains show the way. Speed with comfort, safety, and economy of operating costs. These were the aims of the builders, aims that have been fulfilled and surpassed. As is usual in the history of transportation, the more spectacular achievements lead to important improvements in more prosaic fields. And that ever-broadening field is in switching, where diesel-powered locomotives show conclusively their dependability and economy. In 1924, a group of important manufacturers collaborated in the production of a 300-horsepower diesel switching locomotive. These demonstrated their superiority over steam locomotives for many kinds of yard operations. But more important than the history of internal combustion switching locomotives is the factual report of the advantages in economy of operation of diesel-powered switching locomotives over steam. All the weight of the diesel-powered locomotive is carried in the driving wheels. This balance gives the most efficient return from locomotive weight and produces high starting tractive effort. Because of the electrical transmission, full horsepower reaches the wheels for starting and for use in lower speed ranges. These factors, weight on drivers, and horsepower availability at all times assure quick and smooth starting of loads with diesel locomotives. It is not necessary to take up the slack. Most railroad switching is done at speeds under 8 miles an hour. The maximum horsepower of a steam locomotive is not reached until the speed is about 30 miles an hour. Diesel-powered locomotives deliver maximum horsepower at these low switching speeds. Hence, 600 horsepower diesels outperform steam locomotives of 2,000 potential horsepower output. Steam locomotives, because they need more frequent and more extensive repairs, are rarely available more than 6,000 hours yearly. Diesel-powered switchers normally are available for 8,000 hours of work yearly, 330 days of 24-hour service. Electromotive Corporation snuff fuel oil for 5 days operation of 24 hours each. This greater availability for work makes it possible for diesel-powered switchers to replace more than the same number of steam locomotives. Their servicing time is almost nothing. General Motors diesel-powered locomotives will operate anywhere a freight car may be handled. Diesel-powered switch engines have clear exhaust even when working hardest. There is no smoke or steam to obscure the view of the operator, and safety is added to by the absence of the fire hazard and by the more comfortable working conditions for the operator, which prevent fatigue and allow concentration on signals. The short, rigid wheelbase of the diesel-powered switcher and the uniform power application make this locomotive much easier to track. Through the high thermal efficiency of diesel engines, 1 car of fuel oil does the same switching work as 12 cars of coal. With diesel-powered switchers on the job, engine house expense fades to a minute part of that spent on steam locomotives. Repairs to steam switchers average more than repair costs to diesel locomotives of corresponding age. Diesel-powered locomotives do not have to be supported by water treatment plants, water storage tanks, fire dropping pits, cinder disposal facilities, coal hauling facilities, and coal docks. Investigation has shown that if the Class 1 railroads of America were to put 3,000 diesel-powered locomotives to work switching and work them 7,000 hours a year for each unit, they would save $52 million. This would give a return of 25% on the investment in diesel power and completely liquidate that investment in 5 years. A total of 12,000 locomotives are in switching service, 27% of the locomotive inventory of Class 1 railroads. The Class 1 inventory in locomotives built for switching is 8,000 units. And so in 1936, 4,000 locomotives originally built for road service were at work switching, work for which they were not designed nor best suited. Obviously, a steam locomotive built for mainline service is more costly to operate in switching service than one designed to meet the peculiar problems in switching. The major railroads of America can save $52 million every year by supplanting old equipment with diesel-powered locomotives designed for switching service. Add to this freedom from bother with worn-out equipment and greater ability to serve customers, the answer can only be increased demand for railroad service, greater revenues, and an assured future in which to grow and to serve. With faith in this future of rail transportation in America, the Electromotive Corporation is busy building diesel-powered locomotives in its factory at LaGrange, Illinois. Here is the majesty of manufacturing. Here is assurance that nothing can stop the progress of diesel-powered locomotives. Here unprecedented speed on rails is built into passenger locomotives. Here unmatched endurance and economy become inseparable qualities of switch engines. This tremendous plant is the first and largest in the world for the exclusive manufacture of diesel-powered railroad locomotives. And yet, the largest factory for the manufacture of diesel locomotives was only the beginning, and the plant additions bear out Mr. Alfred P. Sloan Jr.'s statement. General Motors is demonstrating its faith in the possibilities of the future. We believe that the present trend of applying diesel power to railroad requirements in the form of locomotives, both for road and yard service, is only in its infancy, with wonderful possibilities for growth. The diesel locomotive is spectacular, yes, and much more. It is dependable, hard-working, and economical. These are the signs of the present, which signal for the future full speed ahead.
gods casting fire across the heavens? Explosions of poisonous gases? Lightning was a mysterious and unpredictable force of nature until a few centuries ago when Benjamin Franklin demonstrated that the heavens' fire behaved in the same manner as electricity. The world's foremost electrician, Dr. Franklin. Dr. Franklin?
The doors of wisdom are never shut.
Dr. Franklin, perhaps you would tell us of your electrical experiments.
If you wish to understand electricity, you should begin with the study of lightning. However, I suggest you not attempt my kite experiment. My investigations led me to conclude that lightning was an effect brought about by the flow of electric fluid or charge. Of course, we in the 18th century had no way of explaining that. We knew nothing of the electron theory.
Science has made great advances since you defined electric flow, Dr. Franklin. And even though we have never seen electrons, today we believe we understand how they relate to electricity.
The morning daylight appears plainer when you put out your candle. Perhaps we should begin with the electron.
First, we must imagine one of nature's elements magnified 10,000 million times. If we could reduce the element to its smallest recognizable form, we would discover an atom, a particle so minute that light waves are not small enough to illuminate it and allow us to see it. So small that the point a sharp pencil makes contains 1 quadrillion atoms. Circling around the atom's relatively heavy nucleus are small electrically charged particles called electrons. Because we cannot illustrate the correct proportions of an atom, we must represent the atom structure with a simple model. We can think of the atom as being made up of a group of small, light particles arranged around a heavy nucleus. The lighter electrons carry negative electric charges, and the nucleus carries positive charges. Normally, a state of balance is maintained within the atom. The positive charges in the nucleus equal the negative charges of the electrons surrounding it. When these charges are equal, the atom is in electrical balance, that is, in a neutral electrical condition. It is possible, however, to disturb this neutral condition by adding or taking away electrons from the atom. The unbalanced atom then assumes an electrical charge. Too many electrons produce an overall negative charge. Too few, and the atom becomes positively charged. Now, let's see what can happen when two neutral atoms come together. Some of the outside electrons no longer move exclusively about their original atoms, but circulate about both atoms. If many atoms are close together, as those in a piece of copper, a few of the electrons detach themselves from their original atoms and move freely between atoms in the metal. However, as long as the entire piece retains its normal number of electrons, it remains electrically neutral. Also, like an individual atom, the metal can lose some of its electrons and become positively charged. Or it can pick up more of its normal number of electrons to become negatively charged. If two charged objects are brought together, electrons will flow from one to the other until both are equally charged.
18th century philosophers postulated a theory embracing two kinds of electric fluid, a vitreous electricity, which repels objects, and a resinous electricity, which attracts them. Now, at the time, it appeared there were two forces. I, however, insisted there was only one electric fluid which all objects possessed. Now, it could be removed by rubbing, for example, creating a deficiency. Or objects could acquire an excess of electric fluid. Now, I believe my hypothesis is consistent with the electron theory, which was not established until a century after my experiments. Perhaps your modern-day theories could explain what moves electrons?
When objects are charged, they have a field of force around them. If opposite charges are near each other, a field of attractive forces produces an urge to move them together. When no path is provided between the two charged objects, no electrons can flow. But if a convenient path is placed between the charged objects, the electrical field is established through the path at the speed of light, and electric current flows. That is, the urge is transmitted through the path, and free electrons move from atom to atom in the direction of the more positively charged object until the charges are balanced.
I believed electricity was a positive fluid. Yet you tell me that electricity is the movement of negative electrons.
For now, Dr. Franklin, we'll trace the electron flow from negative to positive objects.
Nonetheless, the establishment of unbalanced charges in matter is an important principle.
That's right, Dr. Franklin. Now, if you will add acid to those wet cells, we can see how this simple principle gives us a continuous source of electricity. To make a wet cell, we place zinc metal in a suitable container. Its atoms are neutral until a dilute acid solution is added. Then, some of the zinc atoms dissolve into the solution, leaving a few of their electrons behind in the metal. This gives the zinc metal a strong negative charge. Next, we put a piece of copper in another container. Fewer copper atoms go into the solution, so its metal becomes only slightly negative. But since the copper has a weaker negative charge, it is positive in relation to the zinc. If we now combine the solutions, the charges in the mixed solution will become equalized. However, the metals, or terminals, will remain charged. The unbalanced condition in the metals can produce a continuous flow of electrons. This flow is called an electric current. Now, let's see what principles are involved when current flows. There are three related factors that affect the flow of electricity: electrical pressure, or voltage; electron flow, or current; and opposition to electron flow, or resistance. First, let us consider the electrical pressure, or voltage. Because nature tries to maintain an electrical balance, there is a tendency for any negatively charged object to throw off or repel its excess electrons, and for a positively charged object to attract electrons. This urge to maintain an electrical balance is what causes electrical pressure, or voltage. And since this electrical pressure is a repelling and attracting urge caused by opposite charges, its force, or pressure, is equal to the difference in the charges. It is therefore called the potential difference. The unit of electrical pressure, or potential difference, is the volt. The voltage, then, represents the difference between the number of electrons at the negative terminal and the number of electrons at the positive terminal. When a suitable path is provided, the voltage causes the electrons, or current, to flow from one terminal through the path to the other terminal. To better understand current, let's review the action of atoms and their electrons in a piece of metal where there are many electrons moving freely from atom to atom in all directions. If an outside electrical pressure, or voltage, is applied to the metal, the electrons will move predominantly in one direction. The average electron movement is from the negative to the positive terminal. This effect is electrical current. Now, let us consider the unit of electrical current, the ampere. 1 ampere represents 6 quintillion 300 quadrillion electrons passing any given point in 1 second. The electron flow, or current, then, is the number of electrons that pass a given point in a given amount of time. And now the third factor, resistance, which depends on the nature of the material through which the electrons must flow. You may recall that in a metal, many electrons move freely about the atoms. Materials in which this takes place are good conductors of electricity. However, even in the best of conductors, some of the electrons collide with the atoms without freeing other electrons, and their movement is slowed down. These collisions are the cause of electrical resistance. In some metals, this type of collision happens more often. Different metals offer different amounts of resistance to the flow of electrons. For example, copper has low resistance because its electrons are set free more easily after the collisions. Therefore, it is considered a good conductor. Iron offers more resistance than copper. Its electrons are not as free to move after collisions with atoms. Therefore, iron's conductivity is less than that of copper. And in some materials, no electrons are free to move around as they are in most metals. All of the electrons stay with their atoms so that no current can flow. Poor conductors are materials such as glass, porcelain, rubber, and our 20th century plastics. But because these substances permit few or no electrons to flow, they are useful as electrical insulators.
It was my advice to my good friend Peter Collinson that during a lightning storm, he stay in the center of a room away from gilt pictures. And good insurance of safety will be to sit on chairs placed on several feather mattresses. And even more effective would be a hammock, supported by silk cord, equally distant from the walls on every side, from the ceiling above and the floor below.
Dr. Franklin, insulators are not the only use we've made of non-conductors. In some metals, resistance to the flow of electrons has been put to practical use. The collisions of electrons set the atoms into violent vibration, making the metal hot. If there are enough of these collisions, the metal will radiate heat and even light, as in the case of Tom Edison's incandescent lamp.
Very convenient.
A direct result of a metal's resistance to the flow of electrons. The unit by which we measure resistance is the ohm. Its value is best understood when it is related to the volt and the ampere. In the relationship, a pressure of 1 volt produces a current of 1 ampere through a resistance of 1 ohm. Dr. Franklin, your investigations into the nature of electricity motivated many others in later years, such as George Simon Ohm.
That's true, yes.
Perhaps you could help us understand the relationship of electrical resistance to electrical current and voltage, which was first expressed by Professor Ohm in 1826.
A brilliant observation by one who kept the light of scientific curiosity burning brightly.
Ohm's law expresses the relationship as a constant proportion.
R is the equivalent of E divided by I.
The resistance in ohms equals E, the potential difference in volts, over I, the current in amperes. Now, Dr. Franklin, let us consider another method of generating a continuous electrical current, this time using magnets.
In the 18th century, those of us who were curious about such matters never considered the relationship between electric charges and the mysterious force that orients the needle of a ship's compass. Learn of the skillful, for he that teaches himself hath a fool for his master.
Dr. Franklin, if you will please sprinkle the iron filings over your magnet, we will be able to observe a pattern of the magnetic field.
Fools need advice most, but wise men are the better for it.
Magnetism, like electricity, has a field of force, and we can easily observe its behavior and formulate basic laws.
Astonishing.
We know that the Earth is a magnet, as is the needle of a compass. And so are minute particles in a piece of iron which we call domains. And we found that when a predominant number of these domains point in the same direction, the iron bar itself becomes a magnet and has a magnetic field. Dr. Franklin, you can easily demonstrate for us an important principle. Materials that can be attracted by a magnet can become a magnet.
Little strokes fell great oaks.
All material of this nature is made up of tiny magnetic domains. On the other hand, some materials, such as copper, have no magnetic domains. These materials we call non-magnetic because they cannot be magnetized. We also know that every magnet has a magnetic field, and magnets can be made in various shapes to provide strong and convenient fields. To understand how a magnetic field is used to generate electricity, let's again observe the electron. Notice what happens when electrons move through the magnetic field. Look again. As an electron enters the magnetic field, it is deflected from its course. The amount of deflection depends on the electron's velocity and the strength of the magnetic field. Previously, we learned that good conductors of electricity have many free electrons. It was discovered that a conductor moving in a magnetic field causes free electrons in the conductor to be deflected at right angles to the magnetic field. If we stop moving the conductor, electrons are no longer deflected. But as the conductor again cuts through the lines of magnetic force, electrons in the wire are again deflected. In effect, these deflections establish a negative and a positive charge at the ends of the conductor. And we now have two charged terminals capable of producing a continuous flow of electric current, just as we had in the wet cell. If we can keep the conductor moving in the magnetic field, we could generate a continuous flow of electricity. The operation of all electromagnetic generators, regardless of size, is based on this simple principle. Electrons are deflected in a conductor moving across a magnetic field.
Nonetheless, we should keep it moving.
And that's what our modern-day turbine generators do, Dr. Franklin. Water is heated and converted to steam.
Of course, then steam can provide the mechanical energy for the movement which is necessary to deflect electrons in the magnetic field.
And electricity can be produced continuously.
Hide not your talents. They for use were made. What is a sundial in a shade?
By connecting a motor to a convenient source, we can use electricity. The motor works as a generator in reverse, converting electricity back into mechanical energy. And the same magnetic principles again apply to motors. Remember that an electron moving across a magnetic field is deflected. Electrons moving in a conductor are deflected by the motor's magnet, causing a force against the conductor. Billions upon billions of these tiny pushes provide a strong force which can be converted to usable mechanical energy by the motor's turning armature. The greater the number of electrons passing through the wire, in other words, the greater the current, the greater the force moving the wire. These forces on current-carrying wires in magnetic fields furnish the power for all electric motors. And in all motors, from the smallest to the most complex, the principle is the same. Magnetic fields deflect electrons flowing in current-carrying wires. This deflection produces a force. In fact, this principle, the interaction between the magnetic field and electrons, is the basic principle of all electrical machinery.
An astonishing explanation of my electric fluid.
Now, let's review the fundamentals.
There can be no gains without pains.
The atoms that make up nature's elements, in the head of a pin, in a pencil, or a person, or the universe, are composed of positive and negative electrical charges. These charges are normally balanced in matter. By unbalancing them, an electrical field is set up. The urge of nature to restore the balance is electrical pressure, which we call the potential difference, or voltage. The response to this urge, nature's action to restore the balance, is a flow of electrical current. Electrical current is the movement of electrons away from objects that acquire a negative charge to objects whose charge is more positive.
At least we should mention the three related factors that affect the flow of electricity.
The electrical pressure, measured in volts, the current intensity, measured in amperes, and resistance, measured in ohms. Whatever the source or the magnitude of electric energy, these factors have the same relationship to each other. These are the simple principles with which we must begin our study of electricity.
Plow deep while sluggards sleep, and you shall have corn to sell and to keep. And now I really must go. But remember, no man e'er was glorious who was not laborious.